today I'm going to share with you some of the first chapter of my dissertation, looking at how climate change reduces population benefits within marine protected areas due to selective effects on species movement. So marine protected areas are really important for species conservation. They're one of the key tools that are used and are characterized usually when they're successful by increased population biomass, better habitat quality, and through spillover to fishing areas, increased fishery yields as well. You also get some really interesting evolutionary effects within marine protected areas. One of these that's very commonly studied is an increase in body size of fish within reserves due to the fact that they're released from the selection pressure in fishing, where fishing targets those larger members of the species. Unfortunately, though, climate change is really threatening these marine protected areas as they are a static, stuck in space area, and climate change is a very dynamic feature in the environment. And this can lead to things such as shifting species distributions. And obviously, species movement is one of the key features for designing marine protected areas. First, from understanding, is the species you want to protect in the area, is it going to remain in the area? And also in terms of designing some of the features of MPAs, such as their spacing and size, with commonly recommended guidelines being that you should protect 2 times the species home range, as this will allow for at least a portion of the population to be fully protected throughout its lifetime. But another interesting evolutionary effect that can occur within these reserves is that species can actually evolve to move less within them. So in a study by Niña et al., they showed just this theoretically. So what you're looking at in these graphs is just a spatial simulation of an area with the red squares indicating, indicating, oh my gosh, oh no, I just screwed things up royally. No, we're good. Anyway, so there's the flash. With the red squares indicating the marine protected areas. And so in this first column, what you're seeing is this is when the MPA is first implemented. And through time, you get a large increase in the heat map. So that darker equals a larger frequency of this low movement allele. So there are a lot of species within the marine protected area that are moving less than the population outside of these marine protected areas. And you get corresponding population density increases too that you expect to see within an MPA. However, in climate change, there's actually evidence from terrestrial range shifting literature that shows that we actually expect to get an increase in species movement rates. So here you can see across some insect and plant taxa that you see some pretty drastic increases on mean speed at species range edges. So I wanted to ask how do these 2 selection pressures kind of interact to dictate species movement rates within marine protected areas, and how does this affect the conservation success for those species? This could be described as a protection paradox, where a stressor for one, or a driver for one selection pressure actually leaves a species at risk to another selection pressure. So in order to do this, I followed Niña et al.'s simulation structure and created a spatially explicit simulation model that basically just walked through the fish's lifespan. We had 3 different phases, with the first one being an initialization phase, where species spawned, juveniles recruited to become adults, natural mortality occurred, and then species moved, which is the key part of this simulation, because we have movement being dictated by these 2 different alleles, a low movement allele and a high movement allele that is decided based on population frequencies within each grid cell at each time point. So in this first phase, there was no fishing, there was no MPA, and the simulation was just allowed to settle. And then we moved on and added fishing into the scenario. I want to highlight that with this simulation, in order for there to be selective pressures on species movement within this MPA, we had to have a very high level of fishing. So this would only apply to species that are overfished. But given that that's the species targeted by marine protection, it seems pretty relevant through lots of things. And we still had this movement phase where we had a low moving fish and a high moving fish that moved about 3 times the rate of the low moving fish. So finally, we get into the fun stuff where we added our MPA in and we implemented 4 different climate change scenarios to get into some of like just mean increases in temperature seen here, and then some different forms of variability such as El Niño or heat waves. And then we included just heat waves and then heat waves with an additional mean increase in temperature to look at how these different features of climate change might affect selection pressures differently. And in order to add a pressure on selection from climate change, mortality became climate dependent. So as the thermal range, as the temperature within the simulation increased past the fish's thermal range, you saw an increase in mortality for the fish in that grid cell with that temperature. So what did I find? Generally, it followed expected patterns. So on the x-axis here, you're looking at time. It's not labeled because we're focusing just on general trends here. And on the y-axis, I have genotype frequency. For the low movement genotype on the top row, the heterozygote on the middle row, and the high moving fish on the bottom row. And following me at all in this no climate change scenario, we had an increase in this low movement genotype and a pretty big decrease in the high moving genotype. However, when climate change was implemented and started to get hot, we see a pretty steep drop off for the low movement allele within only the simulations that had any kind of mean increase in temperature. So the only heat wave scenario more closely resembled the no climate change scenario than the other climate change scenarios, leading us to suspect that it needs some kind of consistent climate change selection pressure to lead to some kind of evolutionary effect. Additionally, as the high moving genotype has already been reduced so much in the population early, we end up with movement rates increasing only through the heterozygote, which could lead to reduced movement ability in climate change. If we look at population densities, which is now again year or time on the x-axis and population density on the y-axis, without climate change, as expected, we get about 2 times the population size within a reserve when movement evolution is present. And this is due to the fact that a smaller moving fish population has higher protection within a reserve of the same size as a species that moves farther. But when we add climate change, we see that by about 25 years into climate change, we already have a pretty substantial reduction in that gap between the no movement evolution scenario, which is the solid line, and the movement evolution scenario, which is the dash. And the biggest feature here is that due to that actually leads to a faster than expected rate of decrease of this population, because not only are they dying from climate change, they're also increasing their movement rates, and that decreases the relative effectiveness of the MPA for that population. And so finally, one more result. Again, time is on the X, and this time we have 3 different locations within the simulation, with the top row being like the low temperature area of the simulation outside of the MPA, the middle row being within the MPA, and the high temperature being the high temperature portion of the simulation. Again, looking at comparing a scenario where the species was allowed to evolve movement rates and a scenario where they were not, represented by the triangles for no movement evolution and the circles for no movement evolution and the triangles for movement evolution across the 4 different climate scenarios. We see that within the MPA, we actually have an increase in population survival with this movement evolution. So populations that can evolve their movement rate do actually live longer within the MPA than corresponding populations that wouldn't be evolving. However, when you look outside the MPA, at least in these mean increase climate scenarios, you actually see that the triangles, which is the evolving populations, are going extinct prior to the evolving populations. So what does this all mean? Our main takeaways were that movement evolution allows fish to survive longer within the MPA, but it does lead to an ecologically trapped population where there's the population goes extinct outside the MPA prior to within the MPA, and that climate change reduces the MPA effectiveness long-term by selecting for these higher movement genotypes. And as a result of this, these populations facing climate change decline at faster than expected rates, even within our largest MPAs in our scenario. And finally, MPAs can possibly constrain species from moving at their full potential, which could be detrimental in the face of climate change. So what can we do about this? We made a few suggestions. First of all, with application to MPA management, we focused on how MPA managers' objective might be really important in designing these MPAs, or whether you want to use an MPA or not. If your goal is to just increase local persistence of a species for a time, then the MPA works great because it extends the time that the fish survives within the MPA. However, if your goal is overall population persistence, you might be inhibiting your species from actually moving and tracking climate change. We also recommend possibly a paired solution with assisted migration. Research has shown that lower dispersal species actually succeed at higher rates with assisted migration. So there may be some kind of solution where we time assisted migration from an MPA when the species has evolved to move less, and then plop them in an MPA further up along where they're back in their temperature happy range, and we see higher success rates there. Finally, I would like to thank Steve and my co-advisor Darcy for their support on this project. And if there is time for questions, I will take them.